Theorem beats. Continuing with the conversation about continuity, we are going to discuss a theorem. As we can see, we're going to look at the intermediate value theorem. So let's get going here. All right. Well, here's the theorem. Let's state it. The intermediate value theorem. Let's suppose we got a function, and very importantly, this function is continuous over the closed interval a to b. So remember what that means. It's continuous everywhere inside the interval, and then it is continuous from the right at a and continuous from the left at b. So we're going to assume that's true for the theorem. And then think of some real number L that is somewhere in between the endpoint output values. That is, there's some number L between f of a and f of b. Then the theorem says there must exist some real number x. Let's call it c, that is somewhere in the open interval. So somewhere in between a and b. So there's some number x so that the function's value at this location x is equal to c has an output equal to that number L that is between f of a and f of b. Okay. Now, in other words, what this is really saying down here at the bottom is that as long as you have a continuous function over a closed interval, then that function must take on every single output value between f of a and f of b over the closed interval a to b. And that's because it's continuous. So we're not going to prove it, but we can kind of justify it here. Just think graphically what this is saying. So here's like some situation where it applies, right? You can see the function here is the entirety of this graph kind of looks like a parabola. Okay, that's my function, f of x as we say. And notice over this interval a to b, the function is continuous. So it's continuous over that closed interval since we have continuity from the right at a and continuity from the left at b. And of course, it's continuous everywhere in between those two values. So what it's saying in this theorem is that, okay, look at the output values f of a and f of b here. Right there and right there. And so you can see this little green strip of the graph that is showing all the different output values between f of a and f of b over this interval. And so what the theorem says is, you know, we're continuous as we need to be. Pick any number L. Say it's right there between f of a and f of b. Then there has to be a value of x between a and b, call it c, such that, of course, right there, f of c is equal to that number L. So you could really pick any number in between f of a and f of b here. So any of these dots that I'm drawing on the green strip, there's always going to be some corresponding value of x in the interval a to b such that the function is equal to that output value. And that's really what the theorem is saying. And we kind of think about why that's true. Well, assuming that the function is continuous, then of course at every value of x, we have that the limit as x goes to this number of the function is equal to the output value of the function. So there's no possibility of any holes, any gaps, any asymptotes that are vertical, anything like that. So the function has to be continuous, and hence it has to obtain all those output values over this interval. So that's really what the theorem is saying. And of course, it's applicable to continuity because it assumes continuity. Now, you may say, other than in theory, how can this be useful to us? Well, as we can see here, it helps us show existence of solutions in certain situations. So assuming again that f of x is continuous function over the closed interval a to b, then of course that's what we need in order for the intermediate value theorem here to apply. And so the theorem applies. But now, moreover, let's assume that we have kind of a more special situation, and that is the values of f of a and f of b have opposite signs. So one of them is negative, one of them is positive. Doesn't matter which is which, but they will assume to have opposite signs here. So according to the intermediate value theorem, because one is positive, one is negative, then the output value of 0 has to be somewhere in the interval a to b as an x value. So that is, there must exist at least one real number, could be more, but at least one, call it c again, in the open interval a to b, such that the function at c is equal to 0. Right? You just think you have a continuous function. Maybe here is a, and the output is negative, right down there below the x-axis. And here is b, and the output value is positive. And since the function is continuous, it has to get from f of a to f of b one way or another, but in a continuous fashion. And hence, there has to be this location of c here for which the function is equal to 0. It has to pass through that x-axis, right? It can't jump over it. So how is that useful? Well, we'll see here in a moment through an example, but just graphically, here's a picture kind of like what I just drew, right? At the endpoint B, the output value f of b is positive in this picture, and at the endpoint A, the output value f of a is negative. And so just like we were saying a moment ago, there has to be some location x is equal to c so that the function's output is 0 over this interval. Because of that, intermediate value theorem guarantees this. So let's take a look at this example here. And we're given the equation x cubed plus x is equal to -1. Right there. The question is, does this equation have a solution in the interval from -1 to 1? So we're not asking what the solution is. We're just asking, does it actually even have a solution? Because we can play all kinds of games algebraically, and perhaps we'll never get anywhere if there is no solution. However, if we know there is a solution that exists, at least one, then we know we can go and look for it. So in order to see how the intermediate value theorem is going to apply to this situation, we're just going to rewrite that equation first of all. Okay, so x cubed plus x is equal to -1. We'll simply add 1 to both sides of the equation, and we can rewrite this as x cubed plus x plus 1 is equal to 0, for instance, right? Same exact equation. Both of those equations will have the same solutions, assuming they exist. Now, since we have a 0 isolated on one side and really a cubic polynomial on the left side, we can think of the left side as some function. Right? Let's think of it as f of x there. So in other words, f of x is equal to x cubed plus x plus 1. And what we're trying to do is figure out if this function is ever 0, and if so, where. Now, this is a polynomial function. Polynomial functions are always continuous for all real numbers, x, as we have previously established. And thus, because this function f is continuous really for all real numbers, say on the real number line r, it follows that f is continuous on the closed interval -1 to 1. And thus, that's our check, right? The intermediate value theorem, if you will, IVT for short, it applies. So we know that we can use the intermediate value theorem here. Now what we're going to do is go evaluate this function at the endpoints and see if we can gather any more information. So let's check it out. What is the value of f at the left-hand endpoint -1? Well, just plug it into our function. That's a -1 cubed plus a -1 plus a 1. And of course, that gives us -1. And more importantly, it's negative, right? So you go, the left-hand endpoint got a negative output value. how about at the right-hand endpoint, f of 1? F of 1 is going to be 1 cubed plus 1, which is 3, and that's positive. And thus, we can conclude that there must be at least one value of x in this interval from -1 to 1, such that the function's output is 0, and thus giving us at least one solution to this equation by the intermediate value theorem. So let's write that down. By the intermediate value theorem, it follows that there exists at least one value of x. Let's call it x is c, and it must be between -1 and 1 here, so that f of c is equal to 0. And thus, there must be at least one solution to the equation in the interval -1 to 1. Now I'm just writing it as open because we already know the endpoints aren't 0, right? And so that's kind of a way that we can use the intermediate value theorem, because that equation that we're given in this situation, it might be pretty algebraically hard to solve, for instance, right? And so now we know there must exist some number in that interval -1 to 1 such that there's a solution at that number, and we use the intermediate value theorem to show this. So there's your intermediate value theorem. We explained it. We showed how we can use it to show existence of solutions. And that's the end of the video. So one more video to go on continuity before we get into rates of change. And that video is coming next. So that's it. Math and Beats. Later.